Hi everybody, following on from last week's tutorials on the theory behind circular motion, we're going to basically go into looking at some applications this week, so a little bit more sort of practical applications and some of the quirks and things that tend to come up in the exams. We're going to cover a few of those along the way. So just to get you started, just want you to recap from last week. I've got a little scenario on the table here. So what I want you to imagine is that essentially you've got a string with a mass on the end. Now the mass is 0.2 kilograms, okay. The length of the string, 0.40 meters, so that's the radius of the circle. And just imagine this is being swung round in a horizontal plane. So essentially, imagine you're swinging it round above your head. It's going clockwise with an angular speed of 10 radians per second. So just want you to get going. Okay, and find three things. Find the tangential velocity, which is v, or the linear velocity, the centripetal acceleration, and the centripetal force. So just pause the clip, okay, using those numbers and the equations that we covered last week, just see if you can work those three things out. Okay, so if you've done it already, look, no expense spared this week. We've gone really technical with folding paper. You should have these solutions. So again, if you want to go through the solutions in full, just pause the clip and have a quick look and just check your values. But hopefully you've got a linear speed of 4 meters per second, an angular centripetal, not an angular acceleration, just a centripetal acceleration of 40 meters per second squared. There's two ways of working it out because we came with two equations for that last week. I would recommend using, in this occasion, A equals omega squared r, because we're given omega in the question. So if you've made a mistake earlier, it doesn't matter. Whereas if you use v squared over r and you've made a mistake calculating v, you could potentially then make further mistakes. But either way, it should come out as 40 meters per second squared. And then the force, I've just used F equals ma. Again, you can use m omega squared r or mv squared over r. And that came out as 8 newtons. Now, what we're going to do is have a little look at what this would look like from the side, because it's a slightly different scenario if we were to look at this from the side view. So just ignore the question for now. We're going to have a little look at that in a second. But essentially what's going on here is we've got our mass, and we've got the point that we're going to pivot around. Now, if we think about the forces acting on this mass, okay, we know we've got a centripetal force, a resultant force, remember that is the resultant force towards the centre. Okay, so that is our centripetal force, so I'll label that FC, and that's the resultant. That's really important. Okay, so that's the resultant force on our mass, but we know that the mass has mass, and therefore downwards we'll be experiencing a gravitational pull, and therefore we'll have weight acting downwards, so mg downwards. Now that means the tension in the string is having to do two things before we draw this on. Okay, it is having to overcome the weight to make sure that this mass isn't moving in a vertical direction, and we've got nothing to say it does in the question, so we're assuming it's stationary in a vertical sense. So it's got to overcome that, and it's got to supply this centripetal force, because that's not a force, remember, in its own right. That is a resultant force on what's there. So something has to be providing that, and that the only thing that's available for that is also the tension. So what we must actually have in this scenario is our tension, our only other force. There's only two forces acting on this mass, weight downwards and the tension of the string. But the tension of the string must counter the weight, so it must go upwards, and it must supply that. So actually our string is not horizontal, like we originally said, but is actually an angle. Okay, and if we just sketch in a few details about that angle, okay, then we've got an angle there, theta, that we can consider going forwards. So we've got two forces acting on our mass, tension in the string, which is actually an angle, so that it can compensate for both the weight and supply the centripetal force. Now, this is still classed as a horizontal circular motion because the circular motion is still in a horizontal plane. It's just that the force that supplies it is not horizontal actually in this context. So that's just something extra to be careful of. Now, finding the tension's actually really straightforward, because this now just uses a bit of trigonometry. Okay, now the centripetal force, the resultant force, is going to be smaller than the tension. That should be pretty obvious just looking at the diagram. The tension has to supply the centripetal force and counter the weight, therefore it's going to be larger than the centripetal force, so expect that. And if we look at this as a right angle triangle, which it makes, okay, if we just look at that, we've got the tension, the vertical component of the tension must be the weight, so that and that section there would be the same. So we can just use Pythagoras to find the tension, which actually makes this problem really straightforward in the end. So we've simply got that, right, T squared equals mg all squared plus our centripetal force squared, and that is usually rewritten to be mg squared plus mv squared over r all squared. Okay, be careful with your squares there as you go forward. And you can then utilise that to find the tension. Weight will be easy to work out, mass times gravitational field strength, and the centripetal force you'll be able to work out using either linear speed, as I've used in that equation there, or of course you can use the angular speed as well instead. Okay, now another important thing to consider here would be the angle. Okay, so to find the angle of this, you've actually got two options for this. Okay, you can just use the forces now. We know that this side of the triangle is mg, this side of the triangle is mv squared over r. Okay, and we can just do, right, tan of that angle is the opposite to that, so mv squared over r divided by mg. And if we've already got the numbers for that, you might find that easier just to put that straight in as is. There is a equation, it's not on the formula sheet, this one, but it is a bit of a shortcut that's quite easy to use if you can remember it. So as we just said, so the tan of that angle, okay, will be mv squared over r, the centripetal force, divided by the weight mg. Okay, so because that's already divided by r, divided by that, and you'll notice that the mass actually cancels out. So this just simplifies down to be v squared over rg. And the point of that being that the only two factors that are variables that would affect the angle that this is at is the radius of the circular orbit or the circular motion and the speed. And the faster you swing it, okay, faster that it's going round, the faster the linear velocity that we've got there, the larger the angle will be from the vertical, I should say, so the closer it will be to being horizontal. The larger the weight, the more it will pull it down, so that will reduce the angle and take it away from being horizontal. Okay, actually the tension being in a horizontal plane. It's actually theoretically totally impossible to get a situation where it would be a completely flat plane that it would be circling in there in this scenario, because there's always some weight, so there's always got to be a component of the tension upwards as well, so that it would never go completely in a horizontal plane, but the circular path, remember, always is in a horizontal plane. Now, simply what I want you to have a go at then is using exactly the same numbers that we did for that first question. Okay, so that, if you can't remember and you can't see it on the screen, we had a radius of 0.4 meters and we had a mass of 0.2 kilograms and an angular velocity of 10 radians per second, which gave us a linear velocity of 4 meters per second. So that's the data from the first one. Have a go at the question on the right there. So it says, find the tension in the string, the angle made by the string from the vertical. So basically you're going to use these two equations with the numbers we've already got and check them. Again, have a little go, pause the video and come back in a second and I'll show you the solutions. Right, so I'm just going to move it up a little bit, I think, just a fraction. There we go. Okay, so there are the solutions for you now. Okay, we've got, should come out with a tension, I've got of 8.2 newtons. Now it was an 8 Newton centripetal force, so it's not a huge amount larger, but it is a little bit larger. And the angle from the vertical, 76.2 degrees. Do be careful with your calculator, because you might have from other contexts in this or from maths have popped your calculator into radians. If you do that, you'll get an answer of 1.33. It's absolutely fine to quote your answer as 1.33, so long as you make sure you've got the unit of radian there. So 76.2 or 1.33 radians, and just noted there is a simple way of going through that, having already known the numbers, but hopefully you've had a go at v squared over rg at that point. Tan theta equals v squared over rg. Not on the formula sheet, is really useful to remember if you can. Right, we're going to move on to another scenario now. Okay, so what we're going to do is look at a different application of horizontal circular motion. Now this one does remain in a horizontal plane to start with. We're going to look at just the idea of car and roundabout. Okay, there's lots of different contexts you can use here. Just because I'm doing a car and roundabout doesn't mean it's limited to that. Okay, but if we consider a car and a roundabout, I've got it, I've said it's cornering at 10 meters per second and it's got a mass of 1,200 kilograms. Okay, so I've just drawn a quick diagram of that. So here's the roundabout. I've got it going anti-clockwise for a change here, and I've drawn a top view and a view from the front as well, just for it to give you sort of the two different perspectives of what's going on there. That's going to be a bit more relevant with where we go with this. Again, just have a go at the questions then. Calculate the centripetal force on the car if the roundabout has a radius of 10 metres or if the roundabout has a radius of 15 metres. So two different radii, and we're going to compare the two, and then just have a think about what actually provides that force. So again, pause the video, have a go, come back in a second, and we will have a look at the solutions. Okay, magic reveal time. Here are the solutions. Okay, so part one with a radius of 10 metres actually came out with a force of 12,000 newtons. Part two with a much larger radius, we've got a reduced force, 8,000 newtons. And those forces are entirely provided in this context by friction. Okay, so that's friction between the car wheels and the road surface in this particular context. Now, there's a couple of important points to make here before we move on. The first being that you will notice that the smaller the radius, the larger the force required, okay, and vice versa. Now, that doesn't mean that you will always get that. The road surface and the car tyres might actually not be able to provide that level of force. They might not be able to reach that value. And what you might find is that if for example, the road could be wet, could be icy, whatever, or it could just be that you're cornering too fast and there just isn't the grip there to provide 12,000 newtons of force. What will happen to the car if that happens? Well, if it's going at a very small radius, as the top one, so small radius and at 12,000 newtons required, if the road surface can't provide that, the car will slip and it will slide out of its circle. Okay, now if the surface is able to sort of supply 8,000, you might find that when you get to that 15 metres, if that's exactly what friction the car and the surface can provide, when you get to 15 metres, it might be at a resuming circular motion at that point. It might find its grip and then follow a path of 15 metres. And if you think about it, that's similar to a concept. If you just imagine maybe a rotating disc, if you put an object on a rotating disc, it will slide outwards and maybe will stick to the surface further out. A classic example is dust on a record, an old record player going round. So as the record goes around, the dust will tend to gather towards the edge of the record because close to the centre, there's not enough friction to hold it. But as it moves out, then it will have enough friction to hold it in its circular motion as it goes around. Okay, so that's really important as we go moving forward as a concept to consider as well. If the road can't supply that force at all, then in all likelihood, of course, the car will actually veer off at a tangent to the circle that it was trying to take and continue in a straight line. Now that brings about another concept that we did briefly mention. I was going to say something about it last week, which is the idea of centrifugal force, not to be confused with centripetal force. Okay, centripetal force is the resultant force on an object moving in a circle. Okay, and that is really important as a concept. Centrifugal force is what we describe as a virtual force, in that it is, again, it's not a real force in its own right. Okay, what it is a force you feel like you're experiencing. And if you imagine that you're in the car, this is sort of the easiest thing. The car's going around the roundabout and it's managing to go around the roundabout, and that's fine. There's enough friction between the tyres and the road surface that it's maintaining its circular motion. Imagine you're sat in the car, okay, and there isn't quite the same level of friction required between you and the seat of the car. So while the car's cornering, quite happily going around the roundabout, you're slipping because there's not enough friction between you and the seat. Okay, now it won't be the same values because your mass will be different, but if there's not enough friction between you and the seat, you will slide and you will try and go in a straight line. The car will go round the corner, you will try and continue straight, which means that you experience the feeling of being thrown outwards. It's not really that. What really happening is the car's moving inwards and you're not. So the car door essentially then presses against you as the car moves around, and that's what forces you around the corner, the reaction force of you and the car door, and that force you experience, the reaction force, is actually the centrifugal force. It's a really important idea in a lot of fairground ride designs. To some of the travelling fair ones that don't have you really fully strapped in, but you don't fall out of them because it's spinning quick enough that it's holding you in with the reaction force as it's going around. So that's the idea of centrifugal force, that feeling you get due to the reaction force of something moving in a circle while you try and travel in a straight line. Okay, now, so we've got the concept here that our car might not be able to provide the friction required to keep it in a circular motion. Now, there is actually a way of overcoming that. Okay, and if we move on to the next sheet, that is to look at the idea of banking the circles. Okay, so we've got our roundabout here, okay, or it could be quite often you'll see banked circles on high-speed test tracks for this very reason. So here's our roundabout, and what we've done is the middle bit of the roundabout can stay flat. We don't have to bank the whole circle, but the bit the car's going round, okay, that has been banked and not on the other side. So this is, again, the top view and the front view, and the sides of the circle we've banked. And what I've done is zoom in on it here, because what we're going to do is consider the forces that are actually acting on the car. Okay, now from the centre of mass of the car, which I'm just going to estimate to be about there, okay, centre of mass of the car, the first thing we're going to have is the weight of the car. And that will act vertically downwards towards the centre of the earth, because that's what weight has to do. Okay, in addition to that, yes, there'll be forwards and backwards facing forces here. We're going to ignore those because we're looking at a lateral view of this. Now, we could still have a frictional component. Now, friction will act, there'll be two as we're drawing it. Of course, on a real car, there'll actually be four, but we're looking at it in 2D. So there'll be a frictional force acting down the slope from both the tyres there. So that's friction, which I'll just label as friction for ease at the moment. Okay, and you'll notice that well, that's still not in equilibrium vertically, certainly not, because friction's slightly downwards, the weight's slightly down. So there must be some upward component here as well, and you'll probably very quickly notice that that must be a normal contact or normal reaction force between the tyres and the road. Again, in reality, there'll be four. We're only going to look at two because of the view we've got. Okay, but from the tyres, there will be this normal reaction force. Now, I'm not drawing it brilliantly there, but those would be at right angles to the surface. Okay, and that's our normal contact force going forward. So that would be a free body diagram for the car from this particular concept. Now, that gets a little bit complicated, and there's a lot to consider there. We've got two frictions, four in reality. We've got two normal contact forces, again, four in reality, and we've got the weight downwards, and we're ignoring any driving force or air resistance drag, all those sorts of things as well. But there's some good news here, because for A-level physics, you don't have to consider friction in a mathematical context at all. Okay, you might have to do a qualitative description of it, as in working out what would happen if friction is available or not in a different context, but mathematically it gets ignored. Okay, and in the questions they'll quite often say if friction is negligible, or ignoring the effects of air resistance or friction, things like that. So they might ask you what effect it would have later and give you a written question on that, but mathematically they're going to leave it out. So what we're going to do is have a look at a scenario where we can do that. So we're going to have a little look at, I took 2 sheets now. Okay, we're going to pick up and have a little look at what happens with a smooth surface. Smooth in physics is a technical term. It's not just a general description of a nice flat surface like the surface of a mirror. Smooth literally means frictionless. So it doesn't mean low friction, it means no friction. Smooth means frictionless, so just be aware of that. In fact, I'll just add a little note there because it does come up from time to time. Okay, and I've got my car, and because I'm going frictionless, okay, I'm just going to simplify it down. I can ignore the friction that we had before. I've still got to consider the weight, okay. I'm going to model it as a point mass, okay, because that makes my life a lot easier. So I'm going to model this as a point mass. I'm going to say, right, my point mass there, just for ease on the diagram for now. Okay, strictly this arrow should come from the centre of mass, okay, but I'm just going to simplify it a little bit for the diagram. So I've still got my weight acting down. And what I'm going to do is I'm going to say, yes, I know there's really 4 normal contact forces, but they all act in the same direction. Okay, we're going to assume on either side of the car they're the same size, so there's no overall moments. I'm not going to worry about that. So I'm just going to combine them all into one, and I'm going to say, right, there's a normal contact force. I'm just going to combine it into one, because that's easy, and we like easy. Okay, so now what does that mean, looking at that diagram? It means we've got 2 forces acting on our car. We've got the weight of the car and the normal contact force. We're ignoring friction and we're not worrying about any forwards or backwards forces in this context. If we look at it, we know the car isn't going to float off the road, nor is it going to sink into the road. So we can immediately come to one conclusion about our car. Okay, we can say, right, if I run the numbers on this, then n cos theta, that is the vertical component of n, has to equal mg. Okay, now it's cos theta, if I just extend this a little bit, because with similar angles, this angle in here is theta as well. Okay, so n cos theta equals mg. Okay, now that we can see from the diagram, there is a horizontal component to n as well, okay, and there's nothing balancing that, which means there is a resultant force this way. Now, that's good news, because if you remember what this was actually all about in the first place, if I just bring this sheet back for a second, what we're after was a centripetal force to keep this in motion, which means we need a resultant force in a horizontal direction, and rather handily, our normal contact force is providing that. By banking the circle, we provided that normal contact force. So I can add that in, and I will do it in a different colour. So that means that we have a centripetal force. Okay, perfect, exactly what we want. So n sine theta is equal to our centripetal force, which, as we know from last week, is actually mv squared over r. And we end up with 2 equations involving n. Now, we don't really necessarily need to know what n is, because there's something really, really handy. Now, the first really handy thing is we have got a centripetal force without friction. Okay, so we don't need friction to keep this moving in a circle. It's provided by the normal contact force now. And what I can do here, if we look at this equation, is actually I'm going to number that one equation number 1, that one equation number 2. And what I'm going to do is take equation number 2 and divide it by equation number 1. So I'm going to do 2 divided by 1. That means I've got n sine theta divided by n cos theta equals mv squared over r divided by mg. The n's cancel. Those comfortable with trig, will already know that sine theta divided by cos theta is tan theta. On this side, the m's cancel, so again, the mass of the object actually becomes irrelevant, and we're left with v squared over rg. exactly the same equation as we had for the mass on the string, which was moving in that conical pendulum sort of motion. So circular motion with that exactly the same equation. So that one that doesn't appear on the formula sheet works for two different contexts. Learn it. Get it in your head. Tan theta equals v squared over rg. Really, really useful. Okay, so let's have a little look. Okay, down at the bottom there, it says calculate the braking angle required to maintain uniform circular motion on a 10 metre radius circuit at 10 metres per second. Same numbers that we used for the first part of the previous question when we had a frictional force requirement of 12,000 newtons. So just pause the video, have a go at that quickly. Okay, so the solution of that one, hopefully you can see it just down at the bottom. Okay, so we've got just using v squared over rg, and we've come out with an angle of 45.5 degrees. Quite a steep angle, to be fair. Okay, all the numbers for everything I've done here have kind of come off the top of my head. You know, whether they're realistic or not isn't the point of the tutorial, just to have a look at how these things work. But what we're saying here is that previously we needed a huge frictional force, 12,000 newtons, to keep our car going in circular motion. Actually, we can completely remove the need for friction if we change the banking angle to 45.5 degrees. This car can turn, follow that circle with no friction at all. Of course, in reality, you will have some friction. Okay, and that's a good thing because that will provide some of that force going inwards. It will support the centripetal force, it will add to it, which means that actually you will need a reduced banking angle because you don't need as much of the normal contact force contributing because some of the friction does. So in reality, you can get a bit of both, a bit of normal contact force, a bit of friction, which means you can reduce the severity of the angle needed. Now, it seems a little bit hypothetical to talk about smooth surfaces. Even icy surfaces have some friction, okay? But just to round off, it's not a total exam trick just to make your life easier. There are actual contexts of this that are particularly useful. Okay, so we're just going to have a little look to finish off at one of those contexts, if I can find the sheet for that. Which I've completely lost. Too many sheets of paper. There we go. Wasn't really worth looking for too much because there's only a title on it so far. Okay, so let's have a look at something that requires banked circles to work. Okay, and they are frictionless. It's a real context, and the one is it's aircraft. Okay, they're not on a road. So an aircraft, if you consider an aircraft, that's my highly technical drawing of an aircraft. Okay, an aircraft from the side view, if it's in straight and level flight, it will have essentially four forces acting on it. Okay, it will have a thrust force forwards, okay, provided by the engines, obviously, depending on the number of engines, depends on how many actual forces there are there, but we can combine it into one. There'll be drag, okay, again, made up of some different components. There's profile drag, skin friction drag, all sorts of different things. But if we just group them all together, drag acting backwards, we've got the weight of the aircraft acting downwards, and therefore we've got to have a force acting upwards that low down the school you'll have called up thrust. Aeronautical engineers would refer to that as lift. Okay, now where those actually come from, there's a centre of lift, there's a centre of gravity, and the drag and the thrust should go through those. So there's no saying that the centre of lift and the centre of gravity are the same point, okay? Hence the need for aircraft to have tails to balance out moments. But we're not going to go into that just now either. Okay, what we are going to consider is, well, that's not exactly the scenario that is a major focus. What we need to do is consider what happens when an aircraft turns. And for that, we're going to just rotate this and just look from the front. So from the front view, so there's our aircraft, make it look a little bit more like an aircraft from the front. We'll give it some wings as well. Okay, there will be lift. Okay, we'll act from both wings. Let's assume it's going to be combined into one, and it's there, and we've got weight downwards. Okay. Now, if you turn a car on a road, you angle the wheels and the direction of friction changes and the car will turn with it. You can't do that on a plane because the plane's not in contact with a surface to do it. Okay, so what you need to do is essentially, if you bank the plane, so let's put the plane into a bank, like that, weight still acts downwards, but the lift now acts at an angle. So the vertical component of the lift will still counter the weight, okay? If it's staying in level flight, it's not changing altitude at all, then the vertical component of the lift will be the same as the weight. Okay, quite often when they bank, they do vary altitude a little bit. But what you'll see is that banking it has now provided a horizontal component to the lift. That horizontal component of the lift acts inwards and provides the centripetal force that will allow the aircraft to turn. So it is a real concept looking at things without friction. It's not just a simplification. There's a really important centripetal force component coming from the lift of the aircraft there. Okay, that's it for the horizontal components. There's obviously, like I said, there's a number of different contexts this can come up with, and when you look at some of the exam questions, which you'll do in the lesson that's coming next, where you'll literally look at a lot of these contexts, you'll see so many different applications. Circular motion is not a big topic in its own right at all. What it does do is link to an awful lot of other topics, so it's really important you get it right, because it does link in so many other places, particularly gravitational fields that we're going to look at, magnetic fields later on, but there's clearly context throughout all of mechanics. There's links in with simple harmonic motion that we'll be looking at soon, and looking back even materials, because as soon as you get into tensions that we talked about earlier in the video, that has an implication there as well. So there's a huge number of contexts. I've even seen this come in with particle physics, and particularly quantum physics, which was a very strange question, but it was there once. So it can link in all sorts of different scenarios. Make sure you get yourself comfortable with it doing those questions tomorrow. Okay, thank you very much. Have a lovely evening.